Good day and welcome to the Malware Reverse Engineering with P-Tree presentation. My name is Tom Bonner, Distinguished Threat Researcher at BlackBerry, and I'd like to show you the P-Tree tool that we've been developing. So we're going to do a quick intro, sort of overview of P-Tree, how it came to life, things like that, look at some of the features and sort of how you install it and use it. And then the bulk of the presentation, we'll dive into the demos. So we're going to do a little sort of walkthrough of the P file format, just a whistle-stop tour, and then look at some of the use cases for P-Tree and how it can assist in sort of helping to ease the reverse engineering process for a lot of people. So P-Tree, it's sort of open source software that we sort of released maybe about a year ago now. Developed in Python and based off of Eero Carrera's P file Python library that you may well have heard of, and built on top of PyQt5. So this actually started life as an internal tool and something that I was using quite a bit, embedded into IDA Pro, the disassembler. Really, what we're sort of trying to do at that point was just sort of present the P file in literally a tree. There was no rainbow view, as you can see on the left-hand side there, just the tree view, and just make it easier to navigate portable executables within IDA, which is something it wasn't brilliantly good at. And then on top of that, it sort of blossomed and grew. And about a year ago now, during the very first lockdown, my children were sat at the kitchen table drawing rainbows to hang in the window as a show of support to like the healthcare workers and key workers in this country. And as I was looking at that, I thought, hang on a minute, that's probably a very nice way of visualizing the structure, the composition of a PE file, and sort of hurried back to my keyboard, and that was the birth of the rainbow view within P-Tree. So it provides a very nice sort of visual indication of the structure of the file at a high level. So quite interesting in a way for doing sort of visual comparisons of malware and just being able to see the composition. So P-Tree comes in a few flavors. There's a standalone application, much like any regular P viewer you've probably played with in the past, like P Studio, P Bear, P View, things like that. So you can view headers and certificates, bits of data like that. It has Capstone, the disassembler, baked into it, so certain addresses and offsets can be disassembled that way. We can export data to CyberChef for further manipulation and processing, which is pretty handy, and do VT pivot searches on just about everything you could search on within a P file. So section names, exports, compilation timestamps, bits and pieces like that. Then we have an IDA Python plugin, which is really where P-Tree started. So not only does it allow you to navigate the structures of P files sort of within an IDB, it also works well with memory mapped P files. And in fact, you can even search an IDA database, find MZP headers, pull out the executables, reconstruct them, rebuild them, and dump them with a new imports table, which is pretty handy, as well as auto-labeling and commenting a lot of structures and details from the P finds back in the IDA database, which is pretty handy. We have recall support as well, and actually volatility is pretty soon on its way. So pretty powerful way to operate against memory dumps. And in fact, recall will allow for live systems as well. So much the same as sort of the IDA version. It can scan the entire address space for executables, pull out any it finds, reconstruct them, including imports and exports, which is something that a lot of the forensic frameworks and platforms haven't really done until now. So we can fully reconstruct them, dump them back to disk, and it makes the reverse engineering and analysis process a lot smoother for any analyst at the end of the day. And finally, the latest big release is focusing on Ghidra, so the open source disassembler from the NSA. Now that's not quite as sort of feature complete as IDA Pro, in that there is no debugger in there yet, but it is coming. So currently, whilst it's only possible in the latest release of Ghidra to sort of navigate the structure of P files and sort of browse about and bits like that, as soon as debugger support is released, it should be possible as well to do the sort of dumping and reconstruction side of things too. As for sort of grabbing P-tree, installing it, it's up there on GitHub. We'll do a quick review of this at the end as well. Pip installable as well, pip install P-tree, and off we go, and pre-installed on Remux as well. So plenty of places in which you can grab the tool and have a play around. So let's dive into the demos then, the fun stuff. First part then, we're just going to do a quick sort of whistle-stop tour of the PE file format. I'm sure a lot of people are quite familiar with it, but for those that aren't, we can do a little tour and have a look about. So here is PE-tree then in its sort of raw form. We've just dumped disk view from sysinternals, quite a popular and well-known executable. So on the left-hand side, the sort of rainbow map there, so we can see the structure of the exe, how large certain sections are on disk. Like the text section looks, approximately 50% of the file here. There's an R data section beyond that containing read-only data and some resources as well. So let's keep sort of digging through. We've got a nice sort of summary at the top, various hashes and bits. They're pivot searchable on VirusTotal too, so we can go off to VT and have a little hunt around on those. Back in then, dive through the headers. So the DOS header is the first part of any portable executable file. We see at the start there, it's got the magic bytes MZ at the top. And beyond that, this is where the DOS stub message is embedded. So probably seen the string before. This program cannot be run in DOS mode. This is basically a 16-bit stub. So any executable back in the old days, Windows 95, running in sort of mixed 16-bit, 32-bit mode operating systems. This stub was there for 16-bit DOS. If you accidentally ran a 32-bit P file on there, it had enough code at the start to print the message. This program could not be run in DOS mode and bail. So that's where that part comes from, purely sort of a legacy thing. However, embedded in there as well, there's a very interesting bit of data sort of stuck in that stub. This has come along sort of more recently since, well, Visual Studio 6 back in the day now. But the compiler, or rather the linker, embeds a lot of information in here now about the tools and the sources and the object files and the linker that was used to actually link and construct the executable. Not a very well documented field. Took us a little while to figure it out back in the day, but I think enough tools are sort of fairly au fait with this now. So yeah, just nice to be able to break that down and show a lot of the tools that were in use in there. We can also see, if it correlates with other information in the NT headers later on. This stub can be spoofed, but at least we can see here, like Visual Studio 2008 in the linker version, Visual Studio 2008 in the rich headers. It seems kind of legit. So yeah, we've got the rest of the NT headers mapped out here. So immediately following on them from sort of the DOS stub is the NT headers containing the signature PE. Surprise, surprise, stands for portable executable. And on from that is the file header, where we find interesting things like which machine types this for. Is it Intel i386? Is it AMD 64 or ARM? Any other processors that P files can run on? Timestamp as well. Again, this can be spoofed, but a bit more on that later. And then into the optional header as well, so we can see things like which compiler and or rather linker was used. We can see the address of the entry point, which was set on at the minute. So the code begins in the .text section. Some other alignment bits and pieces. And yeah, sort of beyond this then, we will end up with the data directories. So this is a nice way for the P file to at least alert the P loader where interesting chunks of data are. So things like the imports. This would be APIs that are imported from DLLs. They're stuffed in a data directory, or rather the pointer to them is in the data directory. All the data directory holds is the pointer in memory and the size. The resources are listed through there, so that's icons, string tables, things like that. There's a security directory entry, so this would tell the P loader where any authenticode signatures are. Debug, just holds some debugging information and sort of where the PDB path is, the program database path, bits like that. Load config, we've got things like stack cookies and bits like that listed there, and IAT, which is the actual table of function pointers itself. So that's resolved by the P loader when it's resolving imports. After that, then we have the sections. So yeah, a number of sections in a P file. First one here being the .text section. You might perhaps think that this contains, strings or text of some sort, but it's actually where the code is put, as we can see from the characteristics on this one being code, execute, and read. Yeah, and we can also see through PE tree here then sort of the overall size, ratio, and entropy of this section as well. So entropy being sort of a measure of, how best to describe it, the average number of bits set per byte across a buffer of bytes. So 8 being every bit set and 0 being every bit unset. So the sort of the higher the value, the more we lean towards 8, the more sort of likely it is that data has been compressed or encrypted or tampered with in some way like that. So yeah, first section, text section, holding the code. Moving on from there, next section, our data holds read-only data. Again, fairly standard name used by most compilers. After that's the data section. So in here goes basically any strings or constants in your code that are, well, just that, defined as constants. So if you're writing sort of a C application and you declare a string as being const, can't be written to or modified, then it's going to end up in our data, and anything that can be written to will end up in the .data section. So this is, data that can be manipulated. Beyond that, we've got the .rsrc section. So this is resources. And pretty much all resources in the file should reside within here. They don't always. Moving on then, we have the import descriptors. So this is a big long list of all of the DLLs and libraries that are imported. I'm going to largely skip over that because it's quite long and boring. Following on from there, the directory entry debug. So like I said before, this holds a few things like the program database path. So we can see this is disk view release, diskview.pdb can be quite handy for some malware for at least sort of tracking them, tracking campaigns and bits. But obviously this information doesn't have to be set, can be spoofed, can be stripped out by the developers. So worth bearing that in mind. Yeah, one interesting thing we see is that there's a timestamp in there. And again, for a lot of DLLs with exports as well, there's a timestamp in the exports descriptor too. Now, not very well known is that, yeah, when malware authors try and basically timestamp their executables, so they will replace the timestamp field perhaps with one, say, from cmd.exe to make it look more legit, or they'll just null it out altogether. There are other places in the P file where there are timestamps, so directory entry debug being one, the exports directory being another. And if we're sneaky with some of our, say, virus total pivot searches, and we put a little bit of a time range in there of a few seconds either side, it can quite often be sufficient to find similar and related samples that haven't had the timestamp altered, for instance. So yeah, that's that side of things. After that, load config directory. Again, like I said earlier, we've got SCH handlers listed in here, stack cookies, things like that. Following on then, we've got the resources. Now this is a fairly interesting one, our disk view bin res. So if we go dump that, hex dump it, we can see quite easily there, that's another MZ executable. We draw out icons as well and show sort of the overall ratio and file format layout. Yeah, moving on from there, just sort of finally the VS version info block. So this will list sort of who's produced the file. Again, all developer sets, so these things could be spoofed. And then finally, the security directory info. So certificates in there, we can export them to CyberChef for processing, which is quite nice. You can dump a little more info out of there. In fact, pretty much anything that can be saved, so sections, resources, bits like that can all be exported to CyberChef. And we can do sort of VT searches on serial numbers and bits like that. Yeah, so that's pretty much it. Top down whistle stop tour of the P file. Here we can see, just based off of this certificate search, we were able to find 1.4 million samples. So, very clearly that was a Microsoft certificate we were looking at. Right, so let's dive on into the next one then. So this is a bit more of a sort of use case then for P-tree. We're going to be looking at injected DLLs with IDA Pro. And in this example, what we have is an APT32 sample. It's been loaded up under MCODS, side-loaded, which is, so MCODS is actually a McAfee application. Now, this could have been any vendor. We'd seen APT32, Target, a bunch of different programs, all with side-loading issues in them. So not just McAfee, there was Symantec, there was Google, and quite a few of the regular players. So I'm not singling anyone out here at all. In fact, I think even back in the day, I have been responsible for writing software that was susceptible to side-loading attacks many years ago. So yeah, I know how it goes. Not singling anyone out. This was just the details of the case. So yeah, what had happened was the threat actor, APT32, Vietnamese threat group, had dropped MCODS, the legitimate signed McAfee executable, on a box. And they then dropped a DLL alongside it that MCODS would actually pick up and load. That DLL would then load up some shellcode. That shellcode would unpack some more shellcode into memory. That shellcode would then unpack a DLL into memory. It would load it itself so that the DLL is not sort of loaded via the normal Windows loader mechanisms. And then finally, that DLL would be used to perform sort of C2 communications after unpacking a final stage. So there was a point in time where we were encountering quite a few of these sort of executables with this multi-layered shellcode, and following the entire sort of execution train through was slow and painful each time. Certainly several hours work to track it all, verify everything, to pull the executables out of memory, to reconstruct them, to look at them, to grab the data we were interested in. Took quite a bit of effort. So what I've done in this particular instance, I've run everything up, MCODS, it's loaded its DLL, it's loaded its shellcode, and then I've attached IDA to it as the debugger, and then taken a memory snapshot. So this saves all of the segments or sort of memory regions back to the IDA database so that you can disassemble them. And what we can do then, sort of after having a little look around and then explore, is right-click within P-tree, search IDB, and that's now going to go off and scan the IDA database looking for DLLs that it can find. As you can see, it's found quite a few. You probably recognize the name of quite a lot of these. We've got things like, version.dll from Windows, Wow64Win. In fact, they're nearly all Windows DLLs apart from a couple that come from our sort of memory defense product. So immediately one stands out, and that's this one with the long sort of GUID looking file name. So let's go and drill into this a little bit more, because this is definitely the one that I'm after. So we can see the structure of it now. A lot of, in fact, the bulk of it just seems to be a resource if we look at it. And if we click on that, we can see it's a very high entropy resource, as we saw by the red there. And we can go and click on it and at least browse it in the IDA database and see the code. If we dig down as well, and this is what I was saying earlier about the export descriptor, if you notice there's a timestamp in there. But quite nicely, this also gives us the name of the DLL at compile time, the DLL entry. So we can quite easily see that now, go and find the entry point in IDA, which wasn't so easy to do before if you were just sort of loading this up and debugging blind. And yeah, the sort of the resource as well at the end is where I know that the final stage payload comes from too. So I know that by being able to navigate to that one quickly and easily, that I can just grab the payload, grab the decryption key, which was the first 32 bytes, and decrypt it. So that's pretty much that one. Let me just go back into the middle a little bit more here. Well, one other thing, one other point to make, which perhaps wasn't so clear and visible here, is that during this scanning process, it's been able to pull in and rebuild the imports as well. So at this point now, we could just right-click, save this PE file back to disk, go and open it in a fresh IDA, and everything is ready to rock and roll. Cool. So next little use case, we're going to look a bit at unpacking. In this case, Empress, but it works well with UPX and other similar unpackers that ultimately sort of largely reconstruct the original executable in memory. So again, I've used IDA Pro for this one, but I actually used the box debugger. So wasn't running this on a live system. Box is pretty much sufficient to emulate enough of the APIs to get unpacking working. So as you can see, fairly standard Empress exe. Most of the data is stuffed in Empress 1, Empress 2 sections. The resources are left unpacked here. So we locate at least the first sort of jump out, as we can see here. This will be where it's jumping back to the entry point, but we search IDB now after it's run up, and we see it's find debug 002, which is a sort of segment in memory. And largely, we've rebuilt some of the import table, but not an awful lot. As you can see, there's only one import, or two for kernel 32 per import descriptor. So it's not quite gotten everything, but it's close. So if we right click on this now and hit dump and rebuild imports, add to tree, it's now going to try and rebuild the import table. And what this is going to do is basically scan the code section. So for IDA, it's using the IDA disassembler. For other platforms such as Recall or Volatility, it will use Capstone. Ghidra will use Ghidra. Oh, seem to have gone a bit further. Anyway, so yes, what it's been able to do there is scan all of the code section, looking for any calls, jumps, references that are into any loaded DLLs. We can then resolve the module name and the API name and use that to rebuild the imports table. So this is pretty much done now. If we'd have hit save to file on the last dialog that popped up, the dump dialog, we could have saved it to disk. Again, put that back into IDA. We'd have a fully reconstructed executable. They should run as well. You should be able to double click it and run it, and everything's as it should be. So that's pretty much the Empress use case. After that, we're going to look a little bit now at sort of recall integration and support, and how we can explore processes, DLLs, drivers, any loaded module basically on the system. So to get PE-tree running for recall, it's a slightly different process than perhaps the disassembler, in that we need to start recall first, and then from within it, we can use the run-i command to run PE-tree. And once that's done, it will then be able to connect to recall. It'll be able to enumerate processes. And we can see right here, we've got a full process listing now from the memory dump, all of the drivers listed out under system. So let's go and just pick a few of those. All the user mode processes as well. Here's SVC host and all of the modules, Reader SL, an Adobe app that was part of this. I think this is a Cridex mem dump actually. So they've been dumped out to disk now without sort of a rebuild of exports. We can clearly see that's a driver and the sort of composition of that one. Yeah, Microsoft NetBIOS driver. However, maybe missing imports for that one. So again, much like we did for Empress, rebuild imports, add to P tree, and we should now have a driver with a full imports table on it. So pretty handy to be able to reconstruct the imports for drivers as well. And we can do the same thing for reader SL. I think should have some resources and bits in it that we can get to quite quickly and easily. Very simple to dump anything from memory. It's a much more comprehensive dump process than, say, recall or volatility right now, in that it can fix up a lot more of the headers. It'll remove like certificate directories if they're not there. I think it's definitely a bit better at resetting the section sizes. So what I tend to find is that for sections that may have been modified, .text gets modified for relocations when it's loaded. .data, it's a writable section, things can change in there, but .rdata, .resource, sections like that, even from P files that have been mapped into memory, the checksums can be very good for pivot searching with virus total. So I will often try and locate those sections first and search those MD5s on VT within our own sort of private databases, and see if we get any hits back on those first. Cool. After that, then finally the sort of latest feature release then is Ghidra support. So I'm sure we all know and love the Ghidra disassembler by now. Very much sort of the same as IDA at this point. We can click around. So here, double click on anything on the left view to take you there. Go and see some of the sections, text section there. Go and look at our data. Here we go. We can see it sync up into the disassembly view. It's just very powerful to be able to navigate the P file and at least be able to link it up to the disassembly. At least I found. And again, we can go through and click on resources and view those quite nicely in the Ghidra disassembler as well. And any of these we can pull out and save to disk and send to CyberChef, etc., etc. As I said a bit earlier on, we're hoping the debugger gets released soon. The dumping code is in place; it does work. So, as soon as the debugger is sort of live within Ghidra, then we should be able to do exactly the same sort of dumping, rebuilding of the imports, IAT and IDT that we do with other X's. So yeah, that's pretty much it. We're up on GitHub, github.com/blackberry/p_tree. You can download it and fork it from there. I'm hoping that after this talk, pretty much anyone can go and grab it now. Pip install p tree, off you go, and hopefully this becomes one of your de facto P viewers. I know there are a lot of good ones out there, and I never aim to replace them fully. There are certainly others I use too. For those of you that do use sort of disassemblers and debuggers day to day, I'd hope that you'll be able to grab this and at least be able to do some dumping and rebuild the IATs and IDTs and get malware back into a more sort of analyzable form, if that's even a word. And sort of long term, if people are interested and willing and able, I'm more than happy for anyone to create sort of pull requests on GitHub to contribute to development. Or at the very least, if there's features or you encounter issues and bugs, feel free to create a ticket on the GitHub page, and definitely happy to look into that. So yeah, quick final summary then of everything we've just gone over. So obviously P-Tree is open source tool for reverse engineering or aiding in the reverse engineering of P files. Runs on Windows, Linux, and Mac, which is rather handy. Plugins for IDA Pro, Recall, and Ghidra, with volatility and mini dumps coming fairly soon. We can view, explore, dump, and reconstruct imports in P files. It's up there on GitHub for everyone to enjoy and contribute. And that's it. Thank you very much from me, and thanks for joining. And I hope you have a great rest of the conference. Cheers.